for joining us this evening. I know you're going to love the presentation. Jay was actually brought out to South Africa by the Water Research Council in recognition of his extraordinary expertise in what he really excels in, and that is fluid dynamics. And Jay Harman he's an author, he's an inventor, an entrepreneur, and most importantly, he's a naturalist. And he's had a lifelong passion, studying and understanding how nature, the systems and the methods it uses to streamline fluid flow. And the result of that passion has been a number of innovations that he's developed, but also that has led to the establishment of several very successful biomimicry companies. So we're going to be learning all about that. And the Research Commission, I just want to get their wording correct, is it's really, they brought it out because they are wanting to position South Africa for successful nature-inspired innovations and product development. So it's really being taken seriously now, which is great. And we had the National Biomimicry Workshop in Cape Town, but Jay presented in Joburg as well, and in Cape Town, and then I put up my hand and said, would you please come to Knysna and record in the garden? And they said, we'd love to. And so Jay and Francesca, who's my wife and business partner, thank you so much. Really, really appreciate that. Jay has written this wonderful book called The Shark's Paintbrush, in which he shares his experiences and his adventures in both the natural world and the corporate jungle. And we're going to get a bit of a sense of that from his talk as well. And I think really the most important thing about, and what struck me meeting Jay and Francesca yesterday, is the reason why they do this. And I'd like to quote Ray Anderson, who was the CEO of another biomimicry company called Interface, which is all about carpets. And they have followed an incredible biomimicry journey. But Ray Anderson said, I'd like to challenge people who say that business exists to make a profit. Business makes a profit in order to exist. Surely it should exist for a higher purpose, a higher, nobler purpose. And I truly believe that Jay and Francesca actually epitomize that. So without further ado, oh yes, thank you so much. Yes, we are getting a little bit tongue-tied again, but that is not a problem. Okay, yes, fine. I tend to have several alternative personalities that come out. So it's quite absolutely, yes. Forget the buyer, I'm just a mimic, yeah. No, but thank you so much. We're looking so forward to this, Jay, and really it's been so special meeting you and Francesca, and I cannot thank you enough for joining us down here in this little corner, and we hope you enjoy your stay here. I forgot to thank the people who have made this also possible, which is Belvidere Manor, which has sponsored the venue. They have sponsored the welcoming drink and a meal for us tonight, which is lovely.
Not for all of us.
Not for all of us. No, oh yes, sorry, yeah, sponsored for our guests. And to Action Ads, who put it all out for us, to Knysna Country House, who's provided the accommodation, to Pam Golding, who also helped to promote it all, and last but not least, to Ippy and Susan Kotzer. Where's Susan? Yeah, there, thank you. Who were the absolute stars in making the logistics of this happen. Really, really, really appreciate that. Thank you. And without further ado, there we go, it's very good, I finally got it right. I have over to Jay.
Well, thank you very much, Sue, and thanks for inviting us here. This is a bit of a haul. You'll have to forgive me, I'm Australian, right? But Francesca's American, and I've lived in America. You're Australian? Well, I might wander around a bit tonight. So we're going to tell you a few stories. I think you'll find this interesting, and by the end of it, you'll probably see how relevant it is to right here. But first of all, I have to say that Sue is an extraordinary treasure. We travel all over the world, we speak all over the world, and She is not only a force of nature in her field, but she is a world-class biomimic. So you've got somebody of real note here and real capability. And she asked us to come. Well, there's no way we could say no to that. So we're delighted and privileged. Thank you. So,
can we clap for Sue?
Yes, absolutely.
Since I'm sitting on this side, all the people on this side are going to have to look through you. If you want
Oh,
to,
okay.
if you scooch just probably
I can move.
a foot
How did I
to
do
the
that?
side, just to there, not too far.
Mhm.
I mean, because we don't want to lose you, but
Right.
is that good? No,
There's a window.
So, yeah.
And I have to apologize because I am the one who got us leaving a little later than we thought. We were very confident we'd get here in 10 minutes, but it's not a 10-minute trip. So thank you for your patience, and thank you for probably not to have a heart attack. There you go. We made it safely.
So you might have gathered by now, Francesca is my wife and co-founder of everything that we've been doing for the last 25 years. And she actually runs the show. She keeps the trains on the rails and points me in the right direction and tells me what to say. So if anybody's got any questions about a lot of this, Francesca's the expert on all sorts of aspects. So I'll just start off by saying, well, first of all, how many people here have heard of biomimicry? Oh, great. You've been sowing seeds. Yeah, isn't that wonderful? Okay, well, I'm going to tell you quite a few things here about biomimicry. Some of you may have already heard some of these bits and pieces, but I'm going to show you a lot of the consequences, which I'm sure you probably haven't seen. So, accurately anticipating the future trends can give us incredible advantages economically and politically. And biomimicry is a mega trend. It's probably the biggest trend that humans have ever come across. And it's not just about conservation. I grew up in Australia, and my whole passion in life was nature and conservation. I grew up in a pretty isolated place, wilderness area that was pretty much unspoiled. And I worked for the Fisheries and Wildlife Department in Australia for many years, and decided to take what I was learning from nature into the industrial world to try and help people make more benign tools, because I could just see how much destruction we were doing. So anyway, let's get started. There are more skin cancers in the United States every year than all other cancers put together. And that creates an enormous industry. There are 1,800 products sold in the US as sunblock. And it's a $650 million a year business. The trouble is that most of those sunblocks, almost all of them, don't work very well. They cut out either UVA or UVB, but not both. And the creams that they're in and the lotions that they're in are very often toxic when they're absorbed through our skin. And quite a lot of researchers now are saying they're probably worse, some of them, than skin cancer, or the threat of skin cancer. So, that we share this planet with at least 3 million other species. In fact, a lot of people are saying it could be as many as 100 million other species. And many of those, most of those, have to deal with ultraviolet. So folks have gone out and said, what animal out there, or what animals, could show us something? And some researchers found that our little buddy here produces sweat that is an incredible sunblock. It cuts out UVA, UVB. It's waterproof, antiseptic, antifungal, antiparasitic. It spreads by itself. You put a drop on your skin, it spreads by itself because he doesn't have opposable thumbs to do it himself. And so this molecule is being reverse engineered to create a whole new industry in sunblocks. A $650 million a year industry. This is a huge opportunity for pharmaceutical companies. They're obviously going to have to add something like coconut oil so we don't smell like a hippo's armpit. But so this is an example of biomimicry that's actually turning into product. This isn't a product yet, but it's definitely on the way. So you already know what biomimicry is. It's a design process that defines a problem very carefully goes to nature and says, what's the solution? Just like we're doing with our hippo here. Or somebody's walking across the landscape and stubs their toe on something, looks down and says, wow, there's a solution. I'm going to go and try and find a problem for it. That's what Francesca and I did. Took us quite a few years to find the problems that we could actually address. So here's the thing. We work with a whole lot of biomimics around the world, and we speak around the world. And the collective feeling is, and the collective wisdom is, that there's not a single problem facing humanity today that nature hasn't already solved in millions and probably billions of ways. And she's clean, green, and sustainable. And of course, if we're not sustainable, we're terminal. Right? So we have to get our act together, and we've got this amazing library of incredible examples. So let's have a look at a few of them. We've been looking at, humans have been copying nature for as long as we've had a thought. And if you look at the potter's wasp nest on the left, well, I'd be happy if I could make a pot that good. The paper wasp nest, there's 1,100 species of paper wasp, and they make paper the same way we do today, except we no longer chew it like people did in the first days, but very effective paper. Australian Aboriginals, and they've recently announced in Australia, they kept it under wraps for 10 years while they did the processing, but they found a site in northern Australia where they found tools and campsites and rock paintings, very evolved ones, 60,000 years old. Now I know you folks here, just up the road, are the ancestors to our Australians. In fact, they're all of our ancestors, right? So the 60,000 years, and certainly they've been using boomerangs for a very long time. This is from an aerodynamics point of view, if there are any engineers in the room. Are there any engineers in the room? Oh, good. But if you're an aerospace engineer and you look at a boomerang, it is an incredibly evolved aerodynamic wing. I mean, very clever. Clearly taken from birds' wings. Way back, of course, we had to defend ourselves, and armour was incredibly important. So we had flexible scale armour copying fish and lizard skins and snake skins. Down on the right is Roman copper scale armour. It was used around the world by all sorts of different armies. And right here in Africa, of course, thorny bush was the inspiration for barbed wire in the 1860s when it was invented, and that opened up the entire Western world, the developing world. Imagine America, Australia, Canada, parts of Africa without barbed wire. And camouflage. It's really interesting. Well, I'll come back to it. But camouflage, nature's incredibly good at camouflage, and we as a species have had to be hiding ourselves if we're going on the hunt or if we're in battle or in all sorts of dangerous situations. What an incredible job. And that's a real photograph. That's a real bird. And this one is pretty amazing. Everybody see that? Okay. There's a hunter here with a bow and arrow. So, the modern militaries haven't overlooked this and have really looked into nature and nature's methods for disguise and become so good at it. And this is one reason to apologise. I hate to say this, but in Australia, the military lost one of their trucks because it was so well camouflaged. So it could happen to anybody, right? So they had to advertise in the local community to get help to find their truck. So, anyway, people have been, as I said, looking at nature forever. We were in it, we lived in it, we just copied what nature did. And we've continued that through right to modern times. If you go back to Egyptian times, and you'll see in a little while, I'm going to show you some proportions and designs that nature does. that humans have been using for, we know, at least 50,000 years. The pyramids are built to it, the Greeks used it in their buildings, and the Romans and Renaissance artists. And we've used nature's designs in art and architecture and weaving and pottery right up until current time. But whereas humans were completely focused on nature forever, at the start of the Industrial Revolution, we lost sight of it. We started moving into cities, we started having less interaction with nature, we started getting more cerebral and thinking that we could do better designs, and we actually got way off track in terms of bio-inspiration. But in the 1940s, the new discipline of biomimicry started to emerge, and most of you are probably aware of the Swiss engineer hiking in the Alps in the 1940s, and he was getting, whoops, have we lost that slide?
We took that
I'll
one.
go back. And he got burrs stuck in his socks and on his dog. So he took those burrs under a microscope and invented Velcro, right? So let's go forward. Am I getting ahead of myself? I am getting ahead of myself. Look, I didn't turn the page correctly. All right. See, I'm Australian.
He's the one who said, take out the Velcro slide, they'll all know about Velcro. I took out the Velcro.
Very good.
I'm just thinking behind every great man is a great woman.
Well, that's
A great
Absolutely.
get this, rolling their eyes.
Just as well. Just as well.
So anyway, what's driving the advances in biomimicry today? It was only defined as a discipline, a modern discipline, 20 years ago when Janine Banyas wrote her book, Biomimicry. Well, we're in an extraordinary time in the 21st century. We've got advanced tools like supercomputers and scanners and 3D printers, electron microscopes and chemical sensors, you name it. You know, we've got supercomputers at our company, we've got 2 of them, that are as powerful as the US military had 10 years ago. I mean, the power that's in the hands of the population is incredible. And you know, there's a camera that's being developed at MIT in the US that takes 4 trillion frames a second. Your finger would get tired, don't you think? But extraordinary tools. So what we're able to do is look really deeply into nature and see it at the finest, tiniest levels that we could have never imagined in the past, and extract information. And of course, another driver is environmental crisis. You know, any thinking person on Earth knows that we've got some serious problems, and there are a lot of us that are mobilizing to try and find solutions. And of course, those that actually start to think of biomimicry know that nature is the solver of our problems, and that's where we're looking. So, and then sharing. For the past 15 years, we've had the internet. So anything that we talk about here right now, we can spread around the world in the next 5 minutes if we want to, and inspire each other. So that's having a huge impact, and the rate of change and growth in technology is mind-boggling. Things happening on a daily and by minute basis. And then the other driver that's really important is that there are more graduates today than all of the graduates in history put together. And our young people are looking for solutions. They're not buying into the old stories like we did, especially because they got the internet. And they're looking for solutions, and they're looking for opportunities. Our young always look for opportunities because we're programmed to strive and thrive. So these young, incredibly educated, incredibly informed young people are coming up. They're not in power yet, but it's not going to be long, that are making incredible inroads. So what's the potential? Well, in my opinion, and not just mine, but our colleagues around the world, the overhaul of the entire industrial the overhaul of the entire industrial world without sacrifice. That's an interesting thing, because it's hard to get people to give up stuff. You know, we don't want to give up our comfort or our car, that, you know, whether it's a larger car or whatever it is, we like what we've got. We don't want to use less water if we can avoid it. Of course, we have to use less water, but imagine if we didn't have to, right? We wouldn't. So, so without sacrifice, using far less energy, and I'm going to show you how much less energy we're going to use in the future, creating much, much less pollution, to the point that it's no longer an issue. Far less materials. It's an interesting thing. Nature always achieves the most with the least. Gets the strongest shapes with the least amount of materials. Gets the greatest jobs done with the least amount of energy. And the other thing, from corporate point of view and government point of view, is eliminating liability. Liability is a huge problem in all sorts of industries. So these are early days, and it's really just the beginning of the wave. But the Harman Institute at the Point Loma Nazarene Research Center have been studying biomimicry for the last 10, 12 years. And they've come to the conclusion that there will be $1 trillion of global GDP created by biomimicry in the next 10 years alone, and millions of jobs coming out of it. So this is kind of the greatest secret that nobody's ever heard of, right? And up until about 2 or 3 years ago, we'd go all over the world and people had never heard of biomimicry, but now it's actually entering the vernacular. It's in, they have features on CNN and on the BBC, and it's in Newsweek and Time magazine, so it's happening. So it's the makings of a technical revolution beyond anything that we've ever seen in history. And in all of our lifetimes. I know I'm getting on and I'm impatient, but I'm confident, you know, just seeing what's happening on a daily basis now. So anyway, let's get on to the sharks. So you have a few here, I believe. Francesca and I go diving on the west coast of Australia, which has always been pretty safe, right? But now, I have to say, it's become the shark attack capital of the world. Sorry, South Africa. We had 15 attacks in 11 years. And so now we wear those shark deterrents, and it's really a bit disconcerting. Anyway, sharks are fantastic animals. Typically, when we want to go fast, if we've got a Ferrari or a racing yacht or something, we want to make sure it's completely smooth, and we polish and we polish and we polish. And we test the boat and we pull it out of the water before the race and give it another polish. Nature doesn't do that. Never polishes anything to go fast. And if you look, you know, just a dolphin. When a dolphin's on the hunt and it wants to go fast, it gets goosebumps. Right? And it reduces drag. Now, what's our shark doing? He's got very, very rough skin. It used to be used for sandpaper by cabinet makers. And if you look at it closely, this is what a shark skin looks like. And it's made of the same stuff as our fingernails, and it's really rough. What's nature trying to show us here? The sharks can hit 80 kilometers an hour in the water, which is an incredible burst of speed. At the same time, most of their lives are going very slowly. And you folks are on the coast here, you know that anything that's in the ocean for any length of time that's just sitting there is going to grow weeds and barnacles. Well, the shark can't have that. Well, it turns out nature's got 2 tricks up its sleeve with this shape. At least 2 tricks. There's probably heaps more that we haven't even understood yet. This acts as an incredible lubricant, this rough surface. You've got to build it exactly right. If you don't replicate it, it actually creates more drag and the shark will be slowed down even more. But this actually allows that shark to go much faster. At the same time, and some folks in America have reproduced a version of it in plastic. At the same time as cutting drag, this shape actually stops bacteria from colonizing on the skin. And if bacteria can't colonize, then algae doesn't grow. Algae doesn't grow, then the weeds and the barnacles don't grow. So we have this incredible solution. So these folks over here have created a product, Sharklet, and this is an iPhone case, by the way. And in case you haven't realized, your cell phone is one of the dirtiest things that we own. It's a good thing to wash it from time to time. But if you get one of these cases, bacteria don't colonize on it. And these folks have created plastic films they put on the walls of hospitals and on catheters and furniture, etc. So they can eliminate most of the antiseptics, and they can eliminate the need for washing, for water. It's a great water saver.
Joe,
Yeah.
can you explain why that makes it go faster?
I can. I can in engineering terms, and I'll try and do it in very simple terms very quickly. Normally you've got the water, coming over the surface. But the water closest to it is called the boundary layer, and it experiences drag, right? Just like anything. You put your hand on here and push, you're going to feel drag. So what this does is it interrupts that boundary layer, and it rolls it up, and you'll see a little bit later in the talk why this is important. It rolls up that flow of water into tiny little whirlpools. And those little whirlpools are like ball bearings.
So does it make the boundary layer thinner at the same time?
Well, it kind of eliminates it.
Laminar flow.
It moves from sounds like you know what you're talking about with boundary layer. So it changes it from a drag boundary layer to basically not something you could define as a boundary layer.
It becomes like a ball bearing.
It becomes like ball bearings.
Clear. Amazing.
Jim, if I could ask you, from a biomimicry point of view, diving in that area now, what colour is your wetsuit? Does it look like a seal, or is it coloured like a poisonous fish or a poisonous...
we haven't got there, but some people have done great things, right? There's some folks that have done the black and white bands, because a lot of people nodding, those that haven't heard of it, the pilot fish that swims around the face of a shark doesn't get eaten, black and white bands. So these people created a wetsuit like that and actually tested it. They put it around a whole bunch of offal and things, put it in the water and towed it. And they tried it without the black and white bands, had something like 30 shark strikes, and with the black and white bands, none. So, sounds good. We use the electronic one, the shark shield.
Can the shark, can he wiggle his skin? Or his whatever you call those things?
Oh yes, because it's like scale. It's like fish's scale. It moves all over the place.
But can he deliberately do stuff with it?
No.
Okay, so
well, not that I'm aware of it. If it is, it's probably at a very local sort of twitching muscle level, I would imagine. So.
Now, I was just wondering if by opening it or closing the little scales, he can get different effects.
Right, that I don't know. Yeah, it's quite possible. I mean,
I have to ask a shark.
We'll have to have a look at that. Actually, it'd be worth looking at for sure.
The scientist that originally was working on this is Dr. Anthony Brennan. Originally he was in Florida, state of Florida, when he worked on it, and I mean it's his passion. There's another gentleman named Frank Fish. He's also passionate about studying these large swimming animals. So if you're curious, you could go have a look online. It might be something.
Yeah. Yes.
So can I ask why that pattern inhibits microbial growth?
Well, I'm not an expert on that because this isn't my domain. But I guess because we're actually creating these little whirlpools everywhere, and they're fairly high intensity. So I think that's probably it. Do you know something about that?
It takes a certain number of bacteria to start colonizing and create a biofilm. And those bacteria have to have a certain amount of space to kind of stack up and clump. The ratio on the bottom right, it's a very specific ratio, interrupts their ability to build up enough bacteria touching each other to colonize. So it's the first patent that was ever granted for antibacterial properties based solely on structure. And there's really, Sharplet's website is very good. They have some great little, infographics and things. I mean, very well done. So,
Fantastic product.
Sharklet is the name of the company.
And I think what's also important is that because it repels bacteria, it doesn't put them under threat, so then they don't, mutate to form superbugs or anything like that. So that's a really key part of
Completely
that.
passive.
Good point. Good point.
Completely passive.
So we're consultants to one of the biggest shipping companies in the world, and one of the cruise ship companies. And of course, they have all sorts of strife with norovirus and other viruses. So from their point of view, this is an incredible solution. Put it through all the surfaces that the public are using, they can really, really eliminate a lot of the threat. So, let's move on. Oh yes, I'll move back to him. The Fraunhofer Institute in Germany is so impressed by this that they've actually created a paint and a stencil that if it's put on all the commercial aircraft of the world, we can save 5 million tons of fuel a year.
Wow.
Right? And then there are folks that are looking at putting it on anti-fouling on ships. Because there are more than 55,000 large ships in the world. And by the way, just, ships, anybody here involved with the shipping industry, these big ships, as soon as they get outside territorial waters, are burning bunker fuel, which is like tar from the road. And it is absolutely filthy. In fact, 15 ships produce more pollution every year than all of the world's cars put together. That's a fact. 15 ships. And in fact, we just found this last week, and I thought I'd throw it in. These are the shipping lanes. The Indian Ocean, around the bottom of Sri Lanka and India, across to the Malacca Strait and up to the South China Sea. These are big shipping lanes. And you'll notice these red marks are very concentrated in the Malacca Strait. I sailed into Singapore some years ago on a sailboat, and at that time there were 3,000 ships a day unloading in Singapore. And these lines here, all of this red is lightning strikes. And the lightning strikes over the shipping lanes are caused by particulate matter being put into the atmosphere by the ships burning this tar. So Francesca took this photo in our back garden. Aren't they? They're beautiful, the spider webs. And I like to tell that you often see really raggedy webs and not so beautiful. Well, the beautiful ones are the young ones, and the raggedy ones are the old ones. Spiders that have kind of given up.
Tell me the raggedy ones work better.
Yeah, they might do that. But the interesting thing with spider webs, and maybe Sue, you've told everybody about this in the past, but they don't catch birds. Well, there is one spider in South America that likes to catch birds, hummingbirds. But putting that aside, the rest of the world, the spiders are very civilized. They don't want birds. The way they stop birds hitting their webs is they weave little UV reflectors into them. And a company in Germany has created a glass that replicates this. And that's how we would see the glass. And that's how a bird sees the glass. Now, at the moment in our built space in our cities, there are about 1 billion birds a year that die from hitting the windows. And it's now being tested and shown that if we can refit those buildings, or certainly as we replace those buildings, if we go to this kind of glass, we can save around about 700 million birds a year. We leave out tardies, right? Okay. Yes, well, you covered that beautifully. So anyway, let's look at another one. I'm not going to keep on these. These are just some nice examples of biomimicry, but then we're going to come to the work we do. But this one I think is fascinating. If you can imagine building anything you like, a car, a building, a plane, whatever, with a cork-like material that's lighter than air, 150 times the strength of steel, can support 50,000 times its own weight, it's so strong that you can deform it 80% and it'll bounce back to where it came from. It carries 1,000 times the electricity of copper, 250 times the charge of silicon in our computer chips. It's also one of the most common elements in the universe. You can make a sheet of it 1 molecule thick, and it's complete at that thickness. You can't even see it, right? You see right through it. You can put it on you can stick it onto a glass window and greatly strengthen that window. But at 1 molecule thick, you can cover a football field with a membrane that is completely waterproof and completely gasproof. Never ever leak. And that whole sheet for that whole area, 1 gram, right? So this is graphene. It's worth looking at. Anybody that's interested in investing in the future, it's early days, but there are lots and lots of research happening around the world. Universities, private companies, corporations. We started off with the Stone Age, the Bronze Age, the Iron Age, on to silicon and plastics. The next stage is graphene. And what a use for coal rather than burning it. Turn it into graphene, which can be recycled. The Gates Foundation is so impressed with this and its future that they've got a project to create bulletproof. And we always think this is kind of strange that anybody would describe it as bulletproof. But they're developing a virtually bulletproof, super, super thin graphene condom. So these are just a few examples of form and function, right? But biomimicry is also going into the market in all sorts of material sciences and chemistry and software and nanotechnology and business organization. Oh, that's graphene, by the way. It's no big secret. Lead pencil, you rub it on some paper, you get this smudge, that's graphene. But it's only a few years ago that people worked out, oh, you could get those molecules to hang together and make this phenomenal material. So
Does it take a lot of energy to make that material?
it doesn't really. No, the trick is getting it to, they can make 1 molecule thick membrane. What they've been trying to do is make it into lumps and pipes and stuff like that. We're involved with a program at Monash University in Australia. They've done this on their own, not with our help, but we're hoping to use their product, to commercialize their product. They've actually been able to make it into bricks by copying honeycomb. So another biomimetic thing. So, who doesn't love nature? We holiday in it. We have potted plants in our homes and offices. We have pictures on the walls. We love it. I mean, especially all of us in this room. And it heals us. It's our recreation. And, you know, some researchers put a picture like this on the wall of an exercise yard in a prison. And it cut violence by 50%. Just having a picture there. So what's the biggest, now we'll go on to what we do, right? So what's the biggest source of almost all our challenges in the world today? Well, it's around about energy, right? It's the difference between haves and have-nots, as who's got access to energy at a price that's affordable. And about 1 billion people on Earth do not have access to energy, and they're absolutely the poorest. But at the same time, our leveraging of energy, which has given us this extraordinary wealth and comfort in this age, has also created climate change. And clearly this is an unsustainable situation. We need to change this, and we need to change it really dramatically. And solar and wind are great things, renewables are great things, but they're not really going to solve our problem and avert climate change, not in any short term. By the time we've implemented full solar and wind, and you know, there are forces trying to stop that. In America right now, there's legislation in one of the states to prohibit people using solar. Why? Because they're supporting the fracking industry. And the fracking industry paid for the politicians' campaigns, and they got into power. I mean, we're up against this. I mean, fortunately, there are a lot of intelligent societies on Earth that are not doing that kind of obstruction. Germany's going incredibly far down that road. But we need to move quickly. Now, nature, as it happens, uses at least 75% less energy in its systems than we do. In many cases, it uses about 99% less energy than we do to get the job done. So, here's a fundamental thing where we've taken the wrong step, in my view. So, when I was a kid at school, like all of us, learned that because the shortest distance between this point and this point is a straight line, if we want to use the least energy getting from there to there, we have to go in a straight line. If you want to walk across a football field, go straight. If you go around the side of it, obviously you're going to use a lot more energy. Well, who can argue with that? Of course it's true, it's fundamental, and nobody has ever questioned that. Right? It's a fact of life. Well, when I was a kid, I spent a lot of my childhood swimming in the other side of the Indian Ocean, and I discovered that nature doesn't use straight lines. In fact, we've been working on this for the last 60 years, or I have. Francesca's much younger than me. And I have yet to see or hear anybody show me a single instance where nature has ever used a straight line for anything in this universe. Even the facet of a diamond, if you look at it under an electron microscope, is nothing like a straight line. Okay? So nature never uses a straight line, but it always uses far, far less energy than we do. So there's something going on here. So I noticed that if I grab hold of seaweeds on a rock when the wave's coming and it's pushing me along, and I grab the seaweed to stabilize myself, the seaweeds would break off very easily. I'd have to grab a big bunch of them so I didn't break them. But then, in the wildest storms, huge waves, most of these seaweeds are just fine. They don't break, they don't wash off. And I noticed over a period of time that they're all changing their shape, just like the branches and leaves on the trees when the wind's blowing. And it all looks chaotic. Even a flag on a flagpole looks totally chaotic. You know, there's no real pattern to it, but actually there is. And there's a fundamental pattern, and these seaweeds are all changing their shape to the path of least resistance, least drag. And if you think about it, what do we use all the energy on Earth for? Most of it, not all of it, but most of it is to overcome drag, friction. We try oil and Teflon and all sorts of bearings and things to overcome drag. If we could eliminate drag completely, we'd probably save 80–85% of our energy. Now imagine an aircraft made out of graphene that's lighter than air. Most of it, we wouldn't be, but the passengers. But you've now reduced the amount of energy you have to use to overcome gravity. So graphene plus nature's approach to energy, we're way, way, way down. So anyway, what's happening here? Well, it turns out that there is one shape, and one shape only, that nature uses to move things and to cut drag. And it's never used any other shape since the dawn of the universe. And it's the only shape that occurs. It happens to be the same as the whirlpool in your bathtub when you pull the plug. Now, every living thing on Earth goes through a liquid phase in its development. And while it does that, it actually takes on the geometry of whirlpools. And we see it in every living thing. We see it in seashells and plants, and we see it in firestorms and hurricanes and tornadoes and galaxies, and this is particle decay and a particle accelerator. So the very smallest structures in our universe to the very largest are all in these vortical shapes. For instance, in a tree, every plant actually obeys this rule. This is the cross-section of a fossilized tree. So the growth rings, which normally capture our attention, have disappeared, but we can see where the sap veins have been. Every tree, every plant is pulling liquids and nutrients up its branches and leaves through this whirlpool shape. A whirlpool is a mechanism. It's actually a machine, and I'll explain that. So, and that's why we see things like redwoods, you know, able to pump thousands of gallons of water a day, you know, 100 meters in the air, nearly 100 meters in the air. You see it in the human body. Our heart muscle is the shape of a whirlpool. Our 60,000 miles of cardiovascular system are all in the shape of whirlpools, and our blood is all flowing in the shape of a whirlpool, and when it doesn't, that's when we get into real trouble. This is a seashell, a tongue seashell. This is the cochlea of our ears. This is how we hear as well. And over here is an electron microscope photograph of a human skin pore. This is how we perspire. It's nature's air conditioning system. So, if you take a cross-section, oops, where am I? I'll go the other way. If you take a slice through that whirlpool, there's your whirlpool, you take a slice horizontally, you end up with a pattern that looks like this. It's an equiangular spiral. And here it is here. And the artists amongst us and architects know this spiral. It's called sacred geometry, divine proportion, equiangular spiral. It is the basis of realism in art. The Renaissance artists all knew this. And anything that looks real is built to this proportion. And a plastic surgeon, if it has to reconstruct a traumatized face, or a dentist has to do new teeth, all use this proportion to get the look right. Okay? Our skeletons grow this way. When we breathe in and out, it's exactly the same. We're all using this proportion, and it's in every life form. And there is no movement in air or gas or sap or blood or anything that you can name that doesn't conform to this. And people have sort of seen the mystery of this for a very long time. You know, the megaliths from 7,000 years ago. In fact, the latest ones, Tebeki, what is it? I've forgotten the name. It's in Turkey, 12,000-year-old incredible megalithic structures, all built according to these proportions. So we've seen this forever. And all of the grand buildings, right up until modern time, have all used these proportions, whether it's the pyramids, Angkor Wat, Taj Mahal, the White House, in fact, the Capitol building, Greek buildings, all built according to this. We've just lost it, that's all. And we haven't understood it for what it can give us in the modern age. So, if nature's only using whirlpools, and by the way, if you ask a physicist, he'll say that we live in a turbulent universe. Turbulence is just a collection of whirlpools. And nothing exists except energy. Now, we've all heard that. The mystics will tell us that. The physicists will tell us that. There's actually nothing solid. It's all energy. And all of that energy moves in these shapes. Wow. Who would have thought, you know? So we decided if nature does that, and technology's not doing it, what happens if we freeze a whirlpool and study it? It was pretty hard to freeze a whirlpool, and we spent about 20 years trying to do it, because you can't arrive at this mathematically. And there's a number of reasons for that. Even the greatest supercomputers on Earth cannot give you that mathematically. I won't go into that now, because it'll probably take the rest of the night. But we were able eventually to freeze one, and there it is. And that's the world's first frozen whirlpool. This is a copy of it. It looks like the lily from the garden. Now these veins are the streamlines of a whirlpool. But once we had that, you'd say, well, so what? Right? So this was our solution that we had to find a problem for. And that took quite a few years. Because nobody was applying this to anything, and we had to work out how we might manage to do that. So with this little guy, we went and found ourselves a water tank. Okay, so municipalities are in many countries, and I'm sure you've got them here, store processed water in these tanks, usually on top of a hill so then gravity feed them to your house. And half the water is kept for firefighting and the other half is used for supplying houses. Well, this water in the sun gets hot and quite elevated. And the disinfectants that municipalities use now, as they break down, they turn into fertilizers. So if you've got hot fertilized water, you get biological events. You don't want that, right? That's not good. So the municipalities go out and they tip in a lot more chemistry. So sometimes you can smell it even, right? And so it costs them a fortune. And sometimes, if they get an event going on, they have to dump all this water. We don't want to do that. So these tanks are millions of litres. Or they have to drain it to another tank and use a whole lot of energy to do that and use up this multi-million-dollar piece of infrastructure. So our view was, because the Earth is generally about 50 degrees, 52 degrees, most places of the world.
Fahrenheit.
Fahrenheit, thank you. We figured, well, what if you could circulate this effectively and cheaply? You could homogenize this temperature. You're totally reducing the temperature at the top. You might be able to make a big difference. So we got this little thing, and we put it on a little tripod this high, a little electric motor underneath it. It uses the power of 3 light bulbs. We rotated it at 1200 revs, just spinning it like this. Put it in the middle of this tank. And of course, when we first went to municipalities, they thought we'd been smoking the wrong stuff. We're from California, right? And nobody took us seriously, but eventually a wonderful group of engineers allowed us to do it. We put it in there, and we completely circulated this water body with just this tiny thing. Now, imagine a 40 million litre tank. Getting back to the football field, it's a football field in size, and it's 10 metres deep. That's a lot of water. Now, you're at the football match, and well, you're looking at this tank that's that size, and you put that right out in the middle. You wouldn't think it'd make any difference at all, right? It is so effective that it is now, we actually created a company around this. It is now the leading company in the world at mixing large water bodies. It's by far and away the leading company in North America. There are more than 1,600 of these major installations in the US, the Horn of Africa, Asia and Australia. And it's 100% effective in 100% of applications.
Is that a model or is that the actual
This is one of them. This one's actually been in a tank.
So that's you don't have, the bigger the tank, the bigger the model?
We
No.
thought so.
No. And in fact, we built bigger ones, and the efficiency actually goes down because there's more drag, because there's more surface
It
area.
takes a little longer to set up when you have a smaller piece, but it's the water doing the work. We're just helping it do that.
How much more efficient would that be than, say, a standard prop?
No comparison whatsoever, and I'll tell you why. Because this exactly matches a whirlpool, when you rotate it, you're creating a much, much bigger whirlpool. And it actually turns into a big ring vortex, which is like a donut. Now, all of our emphasis is on whirlpools, because all of nature's is. Here's the buzz. A whirlpool is almost frictionless. It's basically a frictionless machine. Imagine if humans had a frictionless machine. That's what we've got here.
I understood his question was a propeller on a boat, am I correct?
Yeah.
Right, exactly. So if you use a propeller or any other shape, you get a very highly turbulent, what you're doing is you're actually pushing. You know, when nature...
Can I borrow that? I'm going sailing tomorrow.
Yeah, right. We've actually made propellers that you can pass it around. You know, if you've got boats, if you've got outboards, you hit that throttle. If you hit it too hard, you get cavitation, you go nowhere. You just get a whole lot of white water, especially if you go in reverse, right? And that white water is cavitation. It's millions and millions and millions and millions, billions of little whirlpools, and they're all banging into each other and cancelling each other out and entraining air, because you're actually boiling the water. Because a whirlpool is an accelerator which actually reduces pressure, which actually causes water to boil if you run them fast enough. When you do this, you get no turbulence. All of the energy goes into circulating the water, and the water wants to be in a ring vortex. In fact, if you think about it, you put a kettle on the stove, you've got a ring vortex in there. The hot water's rising. You know, so the atmosphere is full of ring vortices. The thermals that birds ride on. The turbulence we hit in a plane, that's all ring vortices. The ocean's full of them as well.
The question was, how much more efficient is this than standard impeller or propeller? It really does depend on the application, the viscosity and so forth. In this particular case, there are some competitors. Ours is about 85% less energy.
85% less. Yeah.
So that definitely catches people's attention.
So to go back to those ships that are causing all that trouble, can you drive them with this machine?
Yeah.
With this?
We've designed propellers. It's a really, really tough market to get into because you've got a 50,000-ton ship or a 20,000-ton ship. To build a propeller for it, I mean, it's a protracted thing, and one propeller's $250,000. We haven't found a ship builder yet that's willing to take a risk putting a non-tested propeller on the ship. It'll happen, but I think we've got better solutions.
What we didn't realize...
Better than this?
I think we've got better solutions than trying to put any kind of a propeller on a ship.
What we didn't realize, well, Jay knew because he's been in boats for a long time, is that especially these large ships, they actually create their own environment because they're pulling so much water through. As
Boundary layer.
So each propeller for those ships is custom designed. So then you're getting into the custom propeller business, but your prototypes are $250,000 each. So this is a big company job. We're a small research firm. So our job is always to partner, to build enough credibility to partner with the big boys that are willing to try it on these large things. And simulation, computer simulation, our supercomputers are terrific, but actually simulating propellers is challenging because you're dealing with not just water flow, but also there's often interaction with the air, and then that, as Jay spoke about, you can churn the water into air. So supercomputers haven't quite caught up to where we could just do it in-house and show them the pretty pictures. So it's one of those markets that'll come toward this.
So we've gone the easier route.
Yeah.
Is there an application for water filtration?
Absolutely, and we'll come to that. Yeah.
Does this little thing that we're passing around, can it also be used to drive something?
Yes.
So,
Yes.
yeah, okay.
What's it painted as? What do you call it?
We call it our lily impeller.
What is it?
Our lily impeller, because it looks like a lily.
That's the
Yeah.
patent that you're...
Oh, the patent is, the actual patent for that one was a rotor with logarithmic scale shape.
Okay, that's just...
Very specifically,
Yeah.
right.
You know, and when you do a patent, you really want to just kind of describe it in as bland of terms as possible, so that the folks that are out there in all of the different patent offices, literally sitting, waiting for the new patents to be issued so they can start to copy them. So it'll just look sort of boring and unimportant. So that was what our patent attorneys slapped on there.
We're very lucky. We ended up with a heap of patents around all of these subjects because, I mean, this is just one expression of it, and there are
Is it
probably
the same?
millions of expressions of it.
Sorry, I mean,
Mhm.
is it the same shape that they're using in the vertical electric
Oh, in the
generator thing? Yeah.
in the turbines,
Mm.
it is not usually the same. Those tend to be more of an Archimedes type spiral, a helical spiral, yes,
Like a web
but
spring.
doesn't tend to have the scoop. We do have one that if you want to go on, Jay, you can talk a little bit about some of our other applications, especially I'm mindful of the time too. We do have a turbine that we're using in the water that has this shape.
So here are some of the things. Now, once you've got a whirlpool, just think about it. All the species on Earth and every snowflake that's ever existed all have these proportions in them. Everything does. Fingerprints, everything does. So once you have this shape, if you change it a little bit, if you squash it, you can change its frequency and amplitude, basically. You can vary its shape a little bit, but you have to have the same proportions in there. And so by changing it just a little bit, you can have an infinite variety of expressions, just like there are an infinite variety of fingerprints and people and snowflakes. So once we had that, we were able to make all sorts of things. And for instance, in water purification, you're talking about filtration. We have a number of things. One is a whirlpool is how nature evaporates the ocean at room temperature. You don't have to boil the water to get the steam, to condense to get fresh water. Nature's pulling it off all the time. How does it do it? It's doing it in cold water to give us that rain. It's doing it by reducing the pressure. Now, if you take a kettle of water to the top of Mount Everest, it uses a lot less energy to boil it than it does down here at sea level, right? Because the pressure is less, the atmospheric pressure is less. So, nature is incredibly good at reducing pressure. Why? Because a whirlpool is an accelerator. If you accelerate air or fluids, it automatically reduces pressure, Bernoulli principle. Conveniently, it also cools. It's a refrigerator as well. So, when you create a device like this, and it looks pretty obvious in a way, it's pretty tricky inside there what goes on, but we're able to boil water at much lower temperatures for much, much less cost. And so we've created one of these. This is the actual unit. We've created one in our laboratory. In fact, it looks like we may be shipping it here. It's a demonstration unit. We're hoping we can, and we've got some contacts into authorities in Cape Town. We think that we can take the cooling water from power stations, let's say the nuclear station down in Cape Town, which is using a swimming pool full of seawater, Olympic swimming pool full of seawater every minute to cool the turbines. And it doesn't get contaminated, it's got nothing to do with the nuclear stuff. And so now they've got this pressurized hot water, they dump it back into the environment. It's actually not good for the environment. We have technology that can take that water and give you 99.99% pure water you can drink. And it can take whatever's left in the, after you've taken that water out, you can take it to a dry state. So now you've got sea salt, which is nice for the table, but sea salt actually has about 120 different minerals and compounds in it that are actually valuable. It even has gold in it. So if you're getting good quantities of totally clean seawater, that's an industry in itself. So that's one example of it, and I'm not going to belabor it. There's a whole lot of things you can do around water, about cleaning up water and collecting water. So we're very enthusiastic about being here in South Africa to talk to whoever's interested in talking about it. The air handling, you know, 22% of the world's electrical energy goes into turning fans to move air. There are billions of fans turning every day of the year. One big user of energy are server farms to run our smartphones and computers and the internet and the cloud, etc. And these server farms in America now are using more than 3% of the national energy, billions of dollars a year. Nearly half of that energy is used to cool the computer racks. It's pretty interesting because nature, you know, this is the supercomputer beyond compare. Human brain never needs cooling. You know, if it does, we're dead. So nature's pretty good at cooling a supercomputer, but right now we have to cool them with fans. And this is currently the best fan that's used, and there's 6 of these on every server rack, so there are millions of these spinning constantly. The state of California and Cisco, was it, asked us to see if we could improve on this. So we applied this whirlpool idea, and there is our retrofit. If you look at it in a little bit, you'll see it doesn't look any different. It's almost the same. They asked us to reduce the energy by 15%. We reduced it by 47%. Right? And we get fans from all over the world, from huge corporations, Ford Motor Company, and all sorts of people. And it's not a fan yet that we've been given that we can't improve dramatically. That's on the air handling side. And there are so many subsections. I'm just telling you some of the bits and pieces, right? High temperature cooling. Now refrigerators, we all use refrigerators, terribly important. They're only invented 100 and something years ago. Before that we had to use salt or smoke or whatever. But refrigerators are terribly inefficient from an energy point of view. And they use refrigerants that are really bad for the environment. And the somewhat cleaner refrigerants cost $1,000 a kilo. So nature doesn't use refrigerants, not at all. If it does, it's water. It doesn't use any other refrigerant than water. So we've created, this is a refrigerator, believe it or not, or it's the mechanism that cools. Now most of this, about 99% of this is not necessary. We just made it like this for a particular application. But we could throw most of this material away. If you look at it in a little bit, with the light behind it, there's a very fine little tube in there. It's kind of like a little whirlpool. I'm oversimplifying it, because a whirlpool is a refrigerator. You think of the hurricanes in the Gulf of Mexico right now. You've got hot ocean water that's up to 88 degrees in some places, and the ionosphere is minus 70, minus 80 degrees. Well, that's Fahrenheit. So nature doesn't like things to get out of balance, and it reacts. It's always looking for homeostasis. So it's trying to balance that differential. It's kind of an immune response, and it's a fascinating thing if you think about it in that way. So we're getting bigger and bigger hurricanes because we've got more and more temperature variation. So that's why we talk about category 5s now, and we're saying these are 1,000-year events. You know, our colleagues say, get used to it. And it's going to get worse, right? As we warm up the oceans. So this is a refrigerator based on that mechanism. Now you imagine you've created a little hurricane in a tube, and you make it go at not 300 kilometers an hour. Let's say you do 3,000 kilometers an hour, or 2,000 kilometers an hour. If you get the tube right, suddenly this thing becomes incredibly efficient as a refrigerator. We don't use a compressor. We put a tiny little pump to this, which is really cheap. We can put refrigerants through it, but better than that, we can put water through it. It's not a swamp cooler, so it doesn't make the area humid. But we can refrigerate, and we can take something at 1,000 degrees centigrade and pull it down to 80 degrees centigrade with this, and in a very short amount of time. In fact, we've been working with a couple of universities with this one, and we've got a demonstration unit at Iowa State University, and it's a metal tube. It's one of these devices, and the way we demonstrate it is our lead scientist has a blowtorch, 2,500 degrees Fahrenheit, and he puts it on the tube until the tube is 2,500 degrees Fahrenheit, and then he takes it off, turns on the cycle, and grabs the tube within 1 second, right? Which, of course, blows everybody's minds. It's phenomenal. This thing works. Now, we'd excuse me, love to get it to air conditioning and refrigeration. We're not there yet. We can get from very high temperatures down to quite high temperatures, but we can't get quite high temperatures down to 0. That's probably another 10 or 20 years of research. We don't know enough to get there yet. But nature does it, creates the North and South Pole, right? There's no trouble refrigerating. So with the right amount of research and intelligence behind it, it can get there as well.
Let me just do a few words on the hydro.
Right. So yeah, I'm going to cut it shorter because I'm going to go on all night if I'm not careful. This is a pump, by the way, just very quickly. It doesn't look like any pump you've ever seen. It models the behavior of the human heart. And it works on suction. You know, we have T-shirts at PAC Scientific that say, nature sucks. And why is that? Because nature actually spends most of its time sucking rather than pushing. And a whirlpool is a suction device. It's a vacuum cleaner. And we've designed a vacuum cleaner that is far superior to anything in the market today based on this. So anyway, these pumps, and the human heart works on suction. These pumps do too. You can pump anything through them. You can pump blood products through them, and we're just starting a joint venture with a major corporation on that. They need a pump that is, what is it, about 1 millimeter in diameter to go inside a tube as a heart assist and to pump blood. 1 millimeter in diameter. So this can pump fish, broken glass, mining slurries, anything. And it's virtually non-wearing, and there's some interesting things around that. The heart doesn't wear out. It doesn't actually, anyway, different story. So up on the far right is our hydro turbine. The US federal government has funded a research program on that for the last 3 years. And this particular one is designed to go into rivers, so you don't have to create a dam. And it's got a number of features. One is that anything going into it comes out. It doesn't hurt fish. Nothing clogs it or damages it. And if you get a typical turbine, and we're putting this on a flexible shaft, so it goes in the water, but the equipment, the generator, can be out of the water. That saves a huge amount of money, not having to waterproof that equipment. So we've got a flexible shaft on it. Now if you do that with any other kind of propeller or turbine blade, the fast-flowing water is going down the middle of the river, out towards the banks. It's much slower because of boundary layer. And a conventional turbine will be tossed out to where there's no work happening. That's just what happens. This one automatically goes to where the most work is happening. And we've found already that this is delivering twice the torque of off-the-shelf turbines. So this is a really significant step. It means that we can harvest energy out of any kind of rivers. First of all, and the federal government's interested in military applications, but more than anything in isolated communities in Alaska, Canada, and wonderfully, the particular department that's funding this is very interested in the developing world. So there are still a lot of people in America that are concerned about the rest of the world, no matter what certain politicians tend to say. Why don't I just stop there? What shall I add in? Okay, I'll go to the next slide. So there's been an explosion of information and understanding about biomimicry just in the last 3 years, as I mentioned. These are new titles that have come out. This is a fantastic book, well worth reading, very interesting. This one, oh, you couldn't get a better book to read. And all proceeds from this go to, we have a non-profit, and all proceeds go to biomimicry education. Now, if you know young people, and we're all young here, this is, it is fun read. You know, it's got a lot of adventure stories, it's got a lot of how we discovered the things that we do, and we also interviewed 100 of our colleagues. So there are 100 case studies in there of other things that people are doing, and amazing things with seashells and maggots and you know, all sorts of things. Not all of them yucky. So biomimicry applies to, and these things, if asknature.org, and Sue really can, I'm sure, has and can supply all sorts of information, but all of those sites are amazing. The Zygote journal here is, has wonderful articles in it, and really the freshest, newest stuff coming off the press. I'll just say this one thing. You know, San Diego has a zoo, and they've done an incredible amount of work, and it's got the backing of a lot of people and a lot of corporations. There are millions and millions, hundreds of millions of dollars being put behind it to create a mini Africa, right? So they have a few hundred acres, and they've got some wonderful animals, and a lot of them endangered animals, but they've got a park, and you can go on a safari vehicle, and you can go through the park, and the giraffe will come up to you and lick your hand, and you know, all the stuff that people love to see. And so San Diego has decided it wants to be America's Center for Biomimicry Research. And we've been through that park, and we got the special tour and everything. And they've done a great job, and top marks to them, right? But then we come here, and you folks have got the real thing. And you're not just limited to a few species, you've got all the species, all the interacting species that depend on each other. You've got the whole thing, the whole biome. Not just the whole biome, you've got thousands of biomes. And, you know, I said earlier, as we know, our ancestors came from up the road here, and we've evolved out of there a little bit, hopefully. I'm not so sure about a lot of things. I'm not sure that we weren't better off in those days, but in some ways. But why shouldn't this area become the world centre for biomimicry? And I'm not just saying that. I mean, you've got it all here, unspoiled mostly, right? Well, that's Sue's vision. And this region, and you've got a champion to do it. And she's thinking that way, and she's got people supporting her in that thinking. This, I mean, imagine what would happen. The attention that you get, the tourism, if you own businesses and things, that's going to be good, right? But you're going to get the kind of attention of people that really love the environment and love animals and really want to sustain life. So I think it's a grand vision, and I think it's really achievable, and I can't think of a better place on earth. There's nowhere else in Africa is as stable as here, that I've seen anyway. I'm really optimistic, and we've offered to support Sue in any way we can. You know, we'll talk to anybody at any level to encourage that. I think it'd be fantastic. So this is the shape of the future. Biomimicry is going to revolutionizing this world, and as I said, nature has already solved every problem that we face. Thank you. Is there time for a few questions?
I hope so, yes. Anyone who might need to leave, I know that there are
Or maybe there's more sherry out there.
I'm sure there is. Please do ask questions.
Jay, one of the largest issues with our wind farms and our solar plants and that is that they don't work when the wind's not blowing or the sun's not shining. All right. And countries that have become more dependent on them are finding that at some point in time they run out of energy. So they still have to have the coal power plants and that. Now, this is probably not a popular statement in this environment, but the science and the physics and the statistics show that nuclear power is by far the safest energy we have, by a long shot. What is your take on it? Because there's no model, to my mind, for nuclear power in nature.
So, this is an area I'm really, really interested in. The fluid dynamics, this is fluid dynamics, the science of fluid dynamics, and a lot of scientists say it's the hardest of all the sciences because people really haven't got a good grip on it yet. You know, study nature and that might. But from nature's point of view, there's no such thing as an energy shortage. There never has been and never will be, because the entire universe is made of energy. Right? Look how much energy you got just to get the Earth spinning. And there's more energy bombarding the Earth in solar power every 7 days or something than we use in an entire year. Nuclear energy had its place. Nature doesn't tend to use nuclear energy, right? And because it doesn't support life. And any consequence that is unintended is catastrophic. And I don't think we humans are smart enough to eliminate risk. So that's my personal view. Now, we're in a world where we need energy. And it is functioning, and I take my hat off to the scientists that are doing this stuff. I really don't think it has a future, and I don't think it needs to have a future beyond its life. You know, if you've got a plant that's got another 20, 30 years, fine. But I think market forces are going to eliminate that. But basically, no one can afford to build a new plant anywhere in the world. Even when people try to make the numbers work, they really don't. So
The key is storage.
storage is for renewables, and that's where enormous amounts of work are going. One of them is batteries, right? So we're doing all sorts of work in batteries. Elon Musk has done incredible things. And you know how smartphones are working now, and electric cars. You know, the Tesla now, the latest Tesla has got 400-kilometer range on one charge, and it can be recharged in 20 minutes. So that means they've got storage doing very well, and he's staked his entire fortune on storage, and he's created the biggest factory in California just on batteries. And here's a nice thing for us, Biomimics, is that batteries, these very high capacity batteries, get hot and they need cooling. This is exactly the device for battery cooling, and we have patents around that. So I think we have to use nuclear while we're getting our act together, but let's put our attention into the other things. That's my personal opinion. Right?
Storage.
And there are other storage systems you probably know. A very effective one in many parts of the world now is they pump water from here up to there. And then at night time, when they don't have the sun or the wind, they let it run down through a turbine. It's a pretty good system.
Is there an example in nature of perpetual motion?
Well, I'd say the universe.
So that leads to my next question. Your lovely lily impeller. The vortex is obviously quite a powerful thing. So if you crank it up a little bit too fast, you could blow the roof off your reservoir.
Well, you know, the thing is that we've found that nothing we're doing is destructive. It's a very interesting thing.
So that gets me back to the perpetual motion. If you could get the water traveling at a sufficient velocity to drive the impeller, could you not then create a situation of...
Well, you know, all I can say to that is that that defies the laws of physics, and I love any idea of doing that. But at the same time, there's a whole lot of reasons why that doesn't work, and there may be ways to not have... No, this one won't, because any mechanical systems on this earth that humans have thought of to date are subject to drag. Even our shark has drag, and this lily impeller has drag. As long as you've got friction, you can't have perpetual motion. And even our, you know, astrophysicists will tell us that the universe at some point has to slow down, and which means that probably the universe is in perpetual motion. But you know, the mystics amongst us, the ones that, you know, when we like to contemplate these things, existence is probably infinite. Our universe may be infinite or may not be. It might be one universe, and then there are infinite numbers of universes. And there's a lot of theory today that supports that kind of thinking. So, what is infinity? Interesting subject.
Even if you don't go all the way to perpetual motion,
right.
I think maybe
We can get pretty good at it, though.
I think the question is maybe pointing to something that I know you and you know your physicist buddies spend a lot of time talking about, which is, can you have what on paper would look like, quote, free energy? And yes, I mean, to answer your question, yes, it may well be that there is enough energy through electromagnetic charge and so forth and so on that we could build machines, not just, when I say we, not just Pack Scientific, but that there are machines that could be drawing not just solar energy, but maybe electromagnetic charge. So yeah, there are folks thinking about this.
And that's my pet subject. So I can tell you one thing: if you get a ring vortex shaped superconductor and put electricity in it, it'll go round and round and round and round for 50,000 years. Right? That's almost perpetual motion. It's not, but it's getting close to it.
So without breaking the laws of physics, the question is valid.
That's very much. Yeah.
This is trying to take vortex thinking and push the edges of current limitations of energy generation.
What would the value of putting the shark skin onto one of your lily impellers be?
Well, I think that's definitely a way to go. We've found rough surfaces on our fans and the things that we build. We've built thousands of prototypes. Thank you so much for coming. Really appreciate it.
I'm sorry we haven't been.
Oh no, I'm glad you've stayed so long. I've been talking and talking here. Good night.
Yeah, it's up to Sue to get the hook. I usually have the big hook and I drag it off, but it's,
No, it's cool.
no, it's good. But
So,
it's a great
yes,
question. It's a great question.
We find typically that if we have rough surfaces, they work better.
It depends on the flow regime that you're working in, and our colleagues that are working on all of those super smooth surfaces, they really are working better in flat surfaces now, or things that you can 3D print, like the catheters and things like that. So they're going forward with their technology, and eventually they'll be able to perhaps etch it into some of our shapes. So it's a matter of catching up to each other.
Right.
And then we can really double up on our...
We're just at the beginning, I think. Honestly, you think of Edison, we're 100 years later. At the time, it was fantastic. They had the World Fair and everybody from around the world came, and they were just blown away by Edison and his new inventions, and he had hundreds of them. And but we look at them now and we say, wow, that's primitive stuff. What we're showing you now, in won't be 100 years, probably 20 years, people will say, wow, that's primitive stuff.
To what degree do you think that Fortune 500 companies are using biomimicry in R&D at this stage?
Well, there's a little bit happening, but not much. And there's a whole number of reasons for that. But I have to, because in-house there's nobody that's educated to it, right? So, and engineers that are engineers that are classically trained are already working 60 hours a day if they want to keep their job. And new stuff is always seen as a risk. You don't want to put new, untested ideas into building a bridge. You want to make sure the bridge doesn't collapse. So you're going to use the tried and tested. So this is what we've been doing for the last 25 years, is breaking down those walls. And now I'm happy to say that we have some of the biggest names in the world that we're working with, the biggest computer company, the biggest maker of automotive parts in the world. We've done work for a Ford Motor Company, GM subsidiary.
I think it's a very important point, and you know, Jay happens to be a good talker, as you've noticed. So we're actually, our day job is to make these devices and work. The Biomimicry Institute, based out of the U.S., and of course they have phenomenal regional groups. They are working with those Fortune 500 companies. Now, you know, they have successes and failures there, because you can, when you've got a corporation so large, as Jay said, the risk aversion is an issue. Just the change that happens in management. So you'll take a project forward a few months, and then you know someone gets moved. So what we recognized early on is, oh, we can't really look to the really big corporations to fund this. We need to prove there's value. So demonstrate value is our internal mantra. Just go, we need to get what they call that cowbell technology that starts to prick up the ears of the folks. Now, we are happy to say that governments around the world they are funding this. So the European Union has billions of euro directed toward biomimetic solutions. You can apply for a grant in Europe and get seed funding to work, and there are thousands of people. I mean, we're talking about
There's at least a couple of 100,000 initiatives happening around the world in biomimicry.
Things that are going on in agriculture, in chemistry, in material science.
Medical.
I mean, this is, what we talked about tonight is drop in the bucket. So in Europe, you got good funding. The United States has, until President Trump was elected, we had a pretty darn good track record. You know, they were actually getting,
Well, they've put millions into our projects for the US
There were
government.
headings in some, you know, they put out these requests for proposals. There was an actual heading for bio-inspired. Well, unfortunately, at this point, the science and technology budget is slashed by 70%. But let's just close our ears and not think about that for a few years. Certainly the trend is there at the government level, so hopefully if the seed funding is there to get past the idea stage to the actual demonstration project stage, then you'll have those large corporations be able to take it up. That's, I mean, we have really
It's almost like
rapid
the advent of electric cars. I mean,
Yeah,
it
that's
took
right.
a long time
That's right.
to get those going.
That's right.
You know, and supported.
Exactly right.
And it's the same thing that you see in any kind of innovation. In that regard, a biomimetic technology is no different. There's this thing called the Valley of Death. You know, you got to go through it, you have to crawl, and then the big guys start looking around and checking out, and indeed, the company that Jay talked about earlier, Pax Water Technologies, one of the largest companies in that municipal water sector in the United States, was watching us for years, you know, and kind of checking us out, and last year they came to us and they said, we can't beat you, we'd like to buy you. So that is what you want.
And they paid twice market value.
Yeah, so that is what you want. So there's a win that starts to be stacked on top of other wins. Interface, they've got nearly $1 billion market, billion US market cap. They describe it as, they say openly 45% of their earnings are coming from biomimetic sources. So when we can stack up 10, 20, 30 of these, Jay thinks, and speaking with some of the leaders at the Institute, we might start seeing that .com bubble. You know,
It'll be a landslide,
yeah.
seriously.
Which
and
is why
people can't not be in it.
When Sue said that she was interested in trying to really grow biomimetic solutions in the actual functioning of this local region, I mean, we said, this is it, man. Get ahead of the game. Get ahead of it and really become that kind of magnet, because the direction is only going toward more and more.
There are universities all over the world
Yeah.
now creating departments on biomimicry, and the leading people in the world are the Chinese and the Indians.
But I would say Biomimicry South Africa, out of Cape Town primarily,
Right.
is already funding PhDs every year, master's students every
Yep.
year. That's
You're already a leader in the world.
Yeah.
I mean, you're in front of America.
yes.
You're way in front of Australia.
Yes,
And that's something to be built on.
yes,
Yeah.
yes.
Way in front.
South Africa.
There's not a single department in Australia.
Because-
I'm an adjunct at...
Why? You know what? Because,
For
first
the
of all,
big body corporate.
no, because South
Petroleum
Africans
companies or-
know in their living memory that things can change. That's what we figured out.
Plus, you got a certain desperation around water,
Yeah.
which makes people look.
And so
Right.
there's been a lot of water research done. No, there's something about the South African
Very
gestalt.
entrepreneurial. I'm new
Yes.
here. I'm married in South Africa.
Mhm.
I find it so exciting.
Yeah.
because It's so entrepreneurial.
No, there's definitely there's a belief that we can try something, and your systems have been a little chaotic sometimes, so that means there are more cracks
Yes,
for
yes,
solutions
yes.
again, whereas the United States, we're sort of over,
Yeah.
we're all kind of bogged down. So no, there's a particular reason why South Africa, and you have people like Claire Janisch, which some of you may or may not know, but you have these champions, as Sue is a champion. that she-
And someone in the Water Research
Yeah,
Commission
is a
who is
champion.
unbelievable.
So you get these champions, they're the pioneers, and it starts to multiply.
Can I just make a point there that you should look up? In Nicholas Taleb's new book, he explains why chaotic societies have a better chance of surviving.
Interesting.
Exactly these
I
things
like
that
that.
are-
I like
Nicholas-
that.
I can
Nicholas
appreciate
Yes.
Taleb.
Yeah.
I can appreciate why my husband doesn't like living in Australia, and
Right.
why I like living here, because
Mhm.
it's
Yeah.
It's kind of wild.
Australia.
So I'm an adjunct professor at Curtin University in Australia, and
Sorry, say that again.
Curtin University, I'm an adjunct. And we're, how
That's
many
in front
years?
of windows.
5 years we've been trying to get them to look at
Do
biomimicry.
one funded project.
It's such a...
Mhm.
So we've got one question.
Yes.
Thank you. You kind of sort of answered it for me there, thank you, but without getting into like conspiracy theory level and all that. But surely, like with your sharklet, this has got massive applications in the medical industry.
Mhm.
In
Absolutely.
terms of wound care,
Yes.
operating,
Mhm.
staff resistant,
Yes.
MRSA,
Yes.
everything.
Yes.
So what's your interest level from Big Pharma, etc.?
Well, and so we
how
are
are we
not
getting this?
we are not the sharklet folks. All right, so that's
They're our colleagues,
they're
but
colleagues of ours.
that's not us.
and
What I
those
specifically want to know is how is this research being made more available and affordable?
yeah.
Thanks.
Well, it came out of university research, and they had U.S. Navy funding, and so the technology belonged to them. They decided to patent it, so they didn't just go the open source route. They looked and looked and looked. Many of these biomimetic technologies are what they call platform technologies. You don't know where to start. So they, just like PACS did a whole matrix and decided, okay, let's get into hospital surfaces. And also because they were still learning how to make their stuff.
Okay.
So flat is easier. All right, what can we put flat things on? The things that you push on to go in and out of bathrooms. That was their very first thing to do. And so they built from there. Then they got a grant to do catheters, and that was successful. So now they're in some kind of kidney work. So it's chipping away. It has not exploded. They have not yet had the big company buy them.
But they've only been in business 4 years,
Yeah.
right?
Okay.
So
So
The
they
treatment applications in this would be amazing.
it's extraordinary.
insane.
Absolutely
Yeah.
amazing.
Absolutely.
It like makes your heart pound to
Yeah.
think about it. Now they're not the only ones working on these antibacterial surfaces, so there are others. And I really can't speak highly enough of the asknature.org website. That's a database that, if you have a particular interest, you can start diving in there and finding things out and finding out how to, make connections.
Yeah,
and
because
learn
like,
more.
because like seaweed dressings were very popular at one point.
Right, right.
Maggots are now
Yeah,
getting popular.
and maggots are, there's a reawakening of that
Yes.
research.
Yeah.
And not just using maggots, but understanding how maggots function,
Yeah,
right?
they're doing.
Yeah.
Actually, if you're interested, the book that I said is a good read. Actually has wonderful stories about all of these things. Lots and lots of incredible things that people are adapting.
One of the challenges in medicine, though, is if you've got to get a small technology that threatens a very big
Yeah.
market, they'll get bought out and then killed.
Yes. That's
Well, we don't let them get killed anymore. I mean, the biomimics we know around the world, we know a bunch of them, are so dedicated.
All right.
I tell you, they just keep hitting it. We've been doing this 25
But
years.
it's
We
also
just
that notion of
won't take
demonstrate
no.
value. Demonstrate value.
But you're right, normally, yeah.
Yeah, so they need to demonstrate the value. I mean, we experienced that straight off the bat when we went to a mining company in Australia early days, showed them our test results, and they offered to buy our patents. I mean, they weren't offering a huge amount, but at the time that felt like a lot. And then the fellow we were talking with said, oh, and by the way, the marketing department says they're buying it and you're not going to see them again because it's worth it to them.
Because they're the biggest maker of mining pumps in the world. You know, a lot of places, if you got water, you crush the rock, you put water in it, you pump the ore. So they have these huge pumps that are $100,000, and they have these big rubber impellers inside that are $30,000, and the impeller lasts 6 weeks. So big business. We took our pump along, it's not going to wear out.
Yeah.
The impeller's going to last for years.
Yeah, so that was a strategic, thing, and these different companies do have to think about that kind of thing. But yeah, the research is really booming. I mean, biomedical research in the bio-inspired space, there are entire university labs focused on that. It's pretty exciting, yeah.
And the fact that there is the circular economy also coming into effect. We're starting to look at completely different systems, different ways of thinking. Philips has been approached by an architect. People are speaking about let's rather rent lux rather than buying lights. So it changes the whole game. It changes the game. So now Philips remains the owner of those lighting bulbs. So now they make them as no more built-in obsolescence. It's designed for disassembly, gathering the material so you can make new ones and that. So I think it's such an exciting space. What biomimicry gives us is the opportunity to make evolutionary leaps because we've got the opportunity to tap into 3.8 billion years of research and development that plants, animals and microbes have done for us. And that's really the essence of it. And that, thank you, Jay, for saying that, we've got the potential here, people, not only to have maybe a, the research and innovation space, an edu-tourism attraction, as well as a region that is showing how we're applying the principles from a systems perspective, because biomimicry is as much looking at models as processes, as well as looking at systems. How is everything functioning within the system? You spoke about how important it is to contribute, that nuclear power doesn't contribute. Any species that has ever lasted on this planet is only one that actually contributes to creating conditions conducive to life. And that is the trick that we need to learn as a species, and that we've got the opportunity here. And we have the opportunity right here in Knysna to become a world first and to become a world leader. And I really hope that having this kind of fantastic inspiration and example of, and dedication and passion and insight is what we could be attracting here at all times.
Attracted us.
And Jay, I can't thank you enough, really. That was extraordinary. And as a very small token of our appreciation. And what I did was I thought, actually, I give you something of the local genius of our place.
Nice.
It's the secret elephants.
I love it.
By a local
Wonderful.
author, thank you. And also just a little thing on our Discovery Park.
Love it.
Yeah.
Thank you so much. That's great. Thank you.
All right. Thank you so much.
And I really want to thank all of you. Honestly, we just love an audience because anybody that listens to this is going to have this in the back of their minds and is going to start thinking this way and maybe see opportunities to get involved in some way or other. And if you've got young people in your lives, absolutely send them in this direction because this is the future. And kids love it. We go and speak to 500 teenagers in auditoriums, and it's like herding kittens, right? It's bad enough with one teenager. We've got 500 of them with their smartphones. And within 5 minutes, the room's silent. And people love it. We give them a slightly different presentation, but they love this stuff. So it's the future. Thank you very much.
Thank you very much.